Welcome to our Quantum Deep Dive. Today, we're diving into the incredible life and the endearing mystery of a true giant of physics, Ettore Majorana.
Yeah, and we're basing this whole deep dive on a really fantastic essay by Jörg Oe Schneppot. It does such a great job piecing together the story of this man who is, well, he was a scientific visionary, but also just a total enigma.
So, we're actually going to start this story not at the beginning, but at the end, or, well, at his disappearance. Picture this. It's the spring of 1938, and a 31-year-old physicist, a guy already seen as one of the deepest thinkers of his entire generation, just vanishes, without a trace.
Right. And that one moment created this legend that has captivated scientists and historians for, almost a century now. But, to really get the mystery, you have to first get the man behind it.
And look, to get a sense of just how big a loss this was, you really only have to hear what his peers thought of him. That quote you see there? That's from Enrico Fermi, Nobel Prize winner, one of the key architects of the entire nuclear age. Not a guy who threw around compliments lightly.
No way. And that's the thing. Fermi didn't just say he was a brilliant colleague. He put him on the same level as Galileo and Newton. Galileo and Newton. So it really makes you wonder, who was this guy who earned that level of respect?
So, that's exactly where we're going to start, with the man they called Majorana, a true genius among geniuses.
So Ettore was born in Sicily back in 1906, and his brilliance was, it was just obvious, right from the start. We're talking about a kid who could solve incredibly complex math problems in his head, faster than an adult could even write them down. He started out in engineering, but he was quickly pulled over to physics, where he found his real home in the absolute hotbed of new ideas that was 1920s Rome.
And in Rome, he fell in with this legendary group called the Via Panisperna Boys, led by the one and only Enrico Fermi. Now, you have to understand, this wasn't just some stuffy university department. It was the epicenter for this brand new, totally bewildering field of nuclear physics. And even among all these brilliant minds, Majorana was just different. His colleagues would tell stories about how he'd sit there silently while they debated some impossible problem. Then he'd just vanish for a couple of days, and then, poof, he'd reappear with a solution that was so perfect, so elegant, it just left everyone speechless.
But for all that genius, he was intensely private. People described him as almost unapproachable, like his mind was just working on a completely different level. He hardly ever published his work, but when he did, wow, it changed the course of physics. And that brings us to his 1937 breakthrough, this absolutely wild idea of a particle that is its own opposite.
Okay, so this is where Majorana really starts bending the rules of reality. In 1937, he publishes what is basically his masterpiece. You have to remember, at the time, physicists were still just wrapping their heads around this crazy idea of matter and antimatter being perfect mirror opposites of each other. But Majorana comes along and asks an even more radical question. He says, okay, but what if some particles don't have an opposite at all? What if a particle is its own antiparticle?
Right. And to really get how revolutionary this was, let's just quickly compare it to the standard idea at the time, which came from Paul Dirac. So a Dirac fermion, think of an electron, has a very distinct, very separate antiparticle, the positron. One's negative, one's positive, opposites. If they meet, boom, they annihilate. But Majorana was suggesting something totally new, a particle that's perfectly neutral, its own perfect reflection. It's like matter and antimatter fused into one single symmetrical thing.
And that right there is the Majorana fermion. So in the simplest terms, it's a particle that is its own antiparticle. The math behind it is just beautiful, really elegant. And that little equation you see, all that's really saying is that the particle's fundamental identity doesn't change, even when you apply the physics that would normally flip a particle into its opposite, its antiparticle. It is a state of just perfect fundamental symmetry.
Now, this wasn't just some, abstract mathematical game. It was a really profound idea. But it was an idea that would basically lie dormant for decades before it came roaring back to life, right at the heart of the most advanced technology we're chasing today. Yeah, for almost 80 years, Majorana's theory was pretty much just a fascinating ghost story for physicists. It was this beautiful, perfect idea, but it had no home in the real world. Nobody could actually find a fundamental particle that behaved this way. It was a ghost hiding in the math, until physicists finally figured out how to build a machine where this ghost could actually show up. A haunted house, so to speak.
And that haunted house is usually a state-of-the-art lab. See, what researchers figured out is that even if they can't find a fundamental Majorana particle, they could create conditions in special materials where the electrons start acting collectively in a way that perfectly mimics one. They call these quasiparticles,
And the hunt for these things is going on in three huge fields. First up, neutrino physics. Here's the big one. If neutrino turns out to be a Majorana particle, it could solve one of the biggest puzzles in cosmology, why there's so much more matter than antimatter in the universe. Then you've got solid-state physics, and, maybe the most exciting of all, quantum computing.
Right, and this is really the billion-dollar idea, using this to build a truly stable quantum computer. The holy grail here is something called a topological qubit. So here's how it works. You create a pair of these Majorana states, but at opposite ends of a tiny nanowire. And here's the magic trick. The quantum information isn't stored in location A or location B. It's stored in the relationship between the two. It's non-local. And what that does is make it unbelievably resistant to noise and errors from the outside world, which is the biggest problem in quantum computing right now. And to do a calculation, you don't just poke at the particles. You physically move them. You braid them around each other. It's incredible. This theoretical ghost from 1937 is literally the blueprint for the next generation of fault-tolerant quantum computers.
It's just an incredible legacy, right? An idea that's echoing across almost 100 years of physics. And that, well, it just makes the end of his own story all the more tragic and all the more mysterious. So, let's go back to his final days. Okay, so it's January 1938. Majorana accepts this prestigious professorship in Naples, a job that was basically created just for him because of his, and I'm quoting here, great and well-deserved fame. But people around him noticed he was becoming more and more withdrawn, really melancholic. It seemed like he was going through a deep personal crisis. And then on March 25th, he gets on that overnight ferry, and he leaves behind these really contradictory letters. One of them hints at some final, unshakable decision, but then another one basically says to ignore the first note. And after that, he just disappears. The trail goes completely cold.
So over the years, three main theories have kind of solidified. The first, and maybe the most straightforward, is suicide, that he drowned himself, driven by that deepening depression. Another theory is that he just walked away from everything, maybe went to live a quiet, anonymous life in a monastery, which, really fits with his reclusive personality.
And then you have the most dramatic theory, escape. Did he flee the country? Some people have speculated he went to Argentina, maybe because he was horrified by the war that was brewing in Europe and was terrified of how his work in nuclear physics could be twisted into a weapon.
The thing is, there's no real proof for any of them, so we're just left with this completely unsolved legacy, where the brilliant scientist and the deep personal enigma are just impossible to separate.
At the end of the day, Ettore Majorana gave us a totally new way to look at reality. A deep, beautiful symmetry between matter and antimatter that, today, is powering the search for the next generation of computers.
But his legacy is really two things at once, isn't it? On one hand, you have this brilliant science that is absolutely central to some of the biggest questions we're asking about the universe. And on the other, you have this profound human tragedy. The story of a mind that could see the universe with such incredible clarity, but maybe struggled to find his own place in it.
His work is absolutely alive today. It's a breathing part of 21st century physics, being chased down in the most advanced labs on the planet. So you're left with these two parallel stories. You've got the ghost and the machine, the ideas that are literally building our future.
And then you have the ghost of the man who just vanished. And that leaves us with the final big question. In the end, what will define Ettore Majorana more? The incredible answers he gave to science, or the one human mystery he left behind that we may never, ever solve?
We hope you enjoyed this quantum deep dive. This explainer was based on the fantastic work of Jörg Schneppert.
Thanks so much for joining us. If you want more information, please do visit schneppert.de. Goodbye.
Schneppert.de is a private project by Jörg Schneppert dedicated to promoting quantum technology. Its mission is to present knowledge in a way that is clear, precise, and transparent for those just starting out, as well as for experts who wish to deepen their expertise. He firmly believes that education and access to well-structured information are the keys to unlocking the full potential of this future technology. If his work helps you realize your own visions and actively and consciously shape quantum technology, then the goal of his project has been achieved.